This is called a heating curve for water, even though it's made of straight lines. Temperature as a function of amount of heat added. So take ice at minus 25 and we add energy to it, add heat. The temperature of the ice will increase until it gets to the melting point. And then the temperature will remain at the melting point until all the ice is melted. So this line 2 represents melting of ice, or the fusion. And then the temperature of the water will start to go up, and it can heat up until you get to the boiling point. And then again, the temperature remains constant until all of the boiling, the vaporization, has finished. And then the temperature of the steam can increase again. We can calculate the amount of heat needed to accomplish this, but in order to do that, we have to do a separate calculation for each straight line and add them together. There's no shortcut way around that. You just have to do an equation for each line. So lines 1, 3, and 5, we have the temperature of a substance changing, right? And so that's going to use the equation we learned back in chapter 7, Q equals mc delta T. So you can look at the change in temperature and the mass of the object or the substance and the specific heat capacity. For line segment 2, you're going to use the heat of fusion. There's no temperature change, so mc delta T is not going to work. And for line segment 4, we're going to use the heat of vaporization. So you calculate for each of those and then you add them together. I'm going to shorten this one up a little bit. Let's go to water at 75 degrees Celsius. So calculate the amount of heat needed to take 1 mole of ice at negative 25 degrees Celsius to water at 75 degrees Celsius. There's lots of variations on this kind of problem. You want to start out with an ugly graph. And the slopes of the lines and stuff don't matter. This is the temperature. That's degrees Celsius, and this is heat being added. And identify the freezing point, or freezing melting point, and the boiling point. And then identify, well, what's your starting temperature? Well, we're starting at negative 25. So that's going to be down here somewhere. So I'm going to start there. And we're going up to 75. So 75 is going to be in here somewhere. And so that's what I'm calculating. I'm calculating that line and this line and this line. We can call this A and B and C. We're going to C. So for A, we have temperature changing, and so we're going to use Q equals mc delta T. Well, we've got 1 mole of ice, so we need to find the mass of the ice in grams. That's going to be molar mass. And then we need the heat capacity of ice. So here we've been given steam, water, and ice, so we need the ice value, 2.09 joules per gram degree Celsius. And then we need the change in temperature. So it's coming from negative 25 up to 0. Delta T is the final minus the initial. So this is 0 degrees Celsius minus negative 25 degrees Celsius. So we can calculate that. $941 8.5 joules. And then for line B, this is the ice melting, and so we're going to use the heat of fusion. So that's this guy right here, 6.02 kilojoules for every mole. We have 1 mole, and we're going to use the heat of fusion, 6.02 kilojoules per mole. The moles cancel out, and I'm going to get 6.02 kilojoules in order to melt the ice. For C, we're back to Q equals mc delta T. The mass is the same, 18.02 grams. Now we have liquid water, so we're going to use 4.18. Joules per gram degrees Celsius. And then the temperature change is we're going from 0 up to 75. So that's 75 degrees minus 0. (18.02) times 4.18 times 75. We need to add these values together, but 2 of them are in joules and 1's in kilojoules. So if I have my 941.5 joules and I want to convert that to kilojoules, I'm going to be dividing by 1,000. So this is 0.9415 kilojoules, and this one is 5.6493 kilojoules. And then I can add those together. That would be 3 sig figs and 3 sig figs. So I'm going to get 12.61 kilojoules of energy needed to do that. You could also be asked, well, how much energy would be released or would need to be removed if you started here and went there, did the opposite? If you have to do a problem like that, I recommend doing it in the forward direction first, and then just changing the sign.